In one of the last videos I showed you how to build a 4-bit adder for unsigned integers. In this video I want to show you how to reuse this 4-bit adder in order to build on top of that a 4-bit subtractor. First of all, we have to do some very minor modification to our existing 4-bit adder. Recall that we used 4 full adders for building our 4-bit adder, and in the picture below you see this building block that we created in Circuitverse, which is hiding these details. So in this building block we just see the inputs that are available for the 4-bit adder, A and B for the operands, and the outputs S for the bit pattern representing the computed result, and this Cout indicating whether the sum is actually representable with 4 bits. Now what we actually need is a third input. Recall that one full adder that we used for adding these least significant bits always had this Cin set to a constant value of 0. And that's why it's not showing up as a possible input, because we never came up with the idea that we possibly could use a different value. And this will change now. We will change this constant input to a variable input so that we can use this building block with a variable Cin for this column computing the sum of the least significant bits. So here you see this demo for the 4-bit adder without the fancy hex displays from last time. Now let's see the details of this building block. So here you have this 4 full adders, and this is this constant input that I was talking about, and this input now gets replaced with some variable input, and this variable input now gets the label Cin. If you check out the layout, you now see that we have 3 inputs, and in the demo for the adder, this Cin we always have the value 0. So here we can use a constant input. But important is that we now have a building block that also can be used with a Cin equal to 1. Before I go a bit more into the details why certain things are actually working, let me just show you first this recipe how to build a 4-bit subtractor on top of this 4-bit adder. In order to compute A minus B, you just have to invert the bit pattern of B and use a Cin equal to 1. Also note that this is of course a very informal description, because we're talking about bit patterns that are supposed to represent certain unsigned integers. But we will talk about that a bit more formal when we're talking about the reasons why things are working, and also this is called the first step because there will be some open questions. But now let me first show you how you can realize this recipe in Circuitverse to better understand what actually needs to be understood in more detail. So here in Circuitverse I basically just created a new demo circuit for the subtractor. Currently it's just a copy of the demo for the adder, but I also added this fancy hex display so that we see now, for example, that it's currently computing 5 plus 2 equals 7, which is correct. Now let's do this recipe. We have to invert the bit pattern of B. Now you have to make sure that you're using here a bit width of 4. That's it. And now I can connect this and this, and now the adder gets the inverted bit pattern of B. And then we also have to change the constant value to 1. That's it. And for demonstration purposes, you also use here a minus sign in this label. Now you see it's computing 5 minus 2, and it seems to be correct because the result is 3. And also 5 minus 3 is correctly computed as 2. But now, of course, there are cases where we cannot represent the result correctly. For example, if we compute 1 minus 3, the result would be negative, and currently we are only talking about bit patterns that represent unsigned integers. So the result cannot be represented. 1 minus 3 equals E. That would be 14, and that's of course not correct. Now also notice that this CF, which indicates the unsigned overflow, is here 0. So this indicates at the current state that we don't have overflow. Now let's go back to an example where the result can be represented correctly. 5 minus 3 equals 2. And here this flag indicates some overflow, which is actually wrong. I mean, in this case, the result can be represented correctly. So the first assumption, and this actually will be correct, is that we just have to invert the state of this bit to indicate the overflow. If it's 1, then we actually have no overflow, and if it's 0, then we actually do have an overflow. So an educated guess would be that for indicating an overflow when doing a subtraction, we just have to invert this bit. So the open questions are, why is this recipe working at all? And how can we indicate an overflow when we do subtraction? Can we confirm our educated guess that we just have to invert this bit from the 4-bit adder? And for answering these questions, I would usually go to the blackboard because we have to do some math. And in this case, I will just switch to the iPad. For describing the algorithm of this 4-bit adder that we implemented in Circuitverse, I was using this scheme. And for the more formal mathematical description, I introduced this notation, which I can use to say that the bit pattern with bits A3, A2, A1, A0 gets identified with the unsigned integer A. And similarly, I can now say with what integer we identify the bit pattern with B3, B2, B1, B0, and S gets identified with this unsigned integer that we get from using here S3, S2, S1, S0. And then I can say what we are actually computing is in general not A plus B, but we are computing S, which equals A plus B mod 2 exponent 4. So that means we now have some kind of a name conflict. We have a plus operator here and a plus operator here. And actually they have a different kind of meaning. Now to resolve this name conflict, to fix it, I will use this notation here with this circled plus for identifying the operation that we carry out with our 4-bit adder. And then I can state what the 4-bit adder is actually doing is this operation with this circled plus applied to the operands A and B. And this is defined in terms of unsigned integer operations on the right hand side here. Now let me also write down that we identify this bit patterns with the integers from 0 to 2 exponent 4 minus 1. So that means all these operands that we use for this circled plus are from this set that I call G, with elements that we know from the integers 0 from 2 exponent 4 minus 1. Now this pair looks familiar. From your first semester you know that this is an abelian group, so we can use some heavy machinery. So these 4 axioms are satisfied. That means in particular that we have a neutral element, which also could be called 0, and actually the element in our set, which we already called 0, has exactly this property. So we could say we know that this element that we call 0 actually is a neutral element. We also know that in a group such a neutral element is unique. So there's just one 0 or just one element with this property of a 0. For implementing the subtraction, it's now in particular helpful that we also know that this axiom is satisfied, that every element has an inverse element, and actually we know that this is also a unique inverse element. Now, whether you want to call this A prime, the inverse element of A prime or minus A, that's actually up to you. I will not use in this video this notation for identifying it, but when we deal with the topic of dealing with signed integers, that's exactly how we will approach things. We will identify a negative number with this property. Now, the idea is obviously, in order to implement subtraction, let's call this circled minus. So A circled minus B, we just have to add the inverse element of B. So we just can define it as A circled plus B prime. And that's actually the idea. So all we have to do is find a way to map this B to this B prime. How to find the bit pattern of B prime if the bit pattern of B is given. And the general method to find this inverse element can be derived by actually a very intuitive method. Note that we formally want to find this B prime so that B circled plus B prime equals 0. But we're actually dealing with the bit patterns, with the bit pattern that is representing B, the bit pattern that is representing the 0. And this is the unknown, and we are looking for a bit pattern which is representing this B prime. Now, I will do this in 2 steps. The first step is just assuming that B is a very specific bit pattern with just ones. And then it's kind of clear what we would have to use in our adder in order to generate the bit pattern for the 0. If I would use this bit pattern, which has only zeros, leading zeros, and the least significant bit is 1, then the problem is solved, because here we have 1 plus 1, that's 0, carry 1, 1 plus 0 plus 1 is 0, carry 1, again 1 plus 0 plus 1 is 0, carry 1, 1 plus 0 plus 1 is 0, carry 1, and the cout is not part of the computed sum. So for that, the problem is solved. Now, assume that I have some other bit pattern, 1, 0, 1, 0. I will not solve the problem in one step. I will not show you how to get exactly the 0 here, but I want to ask you the question, what bit pattern would I have to use here in order to generate a bit pattern with only ones? Because if that problem is solved, we can take advantage of the fact that we modified our adder so that we have some initial carry. So now you can pause the video for a few seconds and think about what bits you have to choose here. And I think it's kind of obvious. You choose a 0 if you have a 1 above, and you choose a 1 if you have a 0 above. And of course, this can be easily proven to work in general. So it's very easy to generate here in the sum a bit pattern with only ones. And that means if I now actually would have this bit pattern here at the top, and I want to use the adder in order to generate here a 0 bit pattern in this part where we actually have this bits for this sum s, I just invert the bits here and use an initial 1 in this cin. And that's it. The bit pattern for B prime is the sum computed with our 4-bit adder of these 2 bit patterns. Now, of course, you can convince yourself that this is actually always working in general. Recall that we are actually computing the sum of 3-bit patterns. And if you look at this column with the least significant bits, you have from this first 2 operands always a 1. And then we add another 1. So we get here a 0, carry 1. And then we have the same situation. We always have 0, carry 1, 0, carry 1, 0, carry 1. And that's why in the end we will always get a cout equal 1. Now we can summarize what we now saw as follows. b circled plus b prime gives 0. And if we want to express this with the integer addition, we know that b plus b prime equals 2 exponent 4, because this cout is always set. And this here is equivalent to b prime equals 2 exponent 4 minus b. Now we can use that to show why this inversion of cout always indicates whether we have an overflow for the subtraction. We define the 4-bit subtraction, this circled minus, as a 4-bit addition with this circled plus, and this in turn is defined as a plus b prime, this is an integer addition, mod 2 exponent 4. And now this equals a minus b plus 2 exponent 4, and this mod 2 exponent 4. Now if b equals 0, it's easy to see that we always have an overflow, because then we have a circled minus 0 equals a plus 2 exponent 4 mod 2 exponent 4. This here is not negative, so that means this here is greater or equal to 2 exponent 4. So you always have a cout equal to 1. For b unequal to 0, then it's positive. A circled minus b equals a minus b plus 2 exponent 4 mod 2 exponent 4. Now this here equals a minus b if and only if this here is non-negative. And that's the case if and only if a plus b plus 2 exponent 4 is greater or equal to 2 exponent 4. So that means we compute actually a minus b if and only if the cout flag is set. So that actually would be it. We have shown, and we can prove it, that this method of inverting the bits of b and using a cout equal to 1 is actually doing a subtraction, and that inverting the cout can be used to indicate whether the result is actually representable with 4 bits. But there is actually one way to get a better intuitive understanding what actually this adder is computing, and also how this subtraction is working. And for that I will use this picture with a circle, and on this circle I will distribute 8 marks. 1 mark for each bit pattern that we can represent with 4 bits. And you see I try to distribute them somehow in an equidistant way. Now I will begin with this mark, and this mark represents the bit pattern with only zeros. So 0, 0, 0, 0. And this will be the next bit pattern when we do counting, 0, 0, 0, 1, and so on. And now in blue I denote how we identified this bit pattern with unsigned integers. So the 0-bit pattern was identified with the 0, this with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now together with this line, I will use this picture to describe what our adder is computing, including this overflow bit. For example, the computation 3 circled plus 2 could here in the picture be described as you start at 3 and you count forward twice. Forward means in this case counterclockwise. And then you end up at 5. That's what you see in the sum of the adder. And if you cross this line here on your way to the result, then you have an overflow, which is not the case here, so we don't have an overflow. But let's say I would use the adder for computing 15 circled plus 2. That means I start here, I count forward, and I end up at 1, so we have this result 1, and we cross the line, so here we have an overflow. And you also can use this for describing the subtractions. Let me just clear here up a bit. Let's say you want to compute 5 circled minus 2. Then the obvious way for us to do this together with this picture would be the following. We start here at 5 and we count back twice. Back means in this case clockwise. We end up here at 3 and we did not cross this line here, so there is no overflow. But that's not how our adder was used for doing the subtraction. We always counted forward, and in this case we would count forward by 14. We end up here at the same number, but we cross the line. So that means if we use the adder for doing the subtraction, crossing the line means we would not have crossed the line when we counted backwards. So we have to invert this bit. Let me give you another example. Let's say I want to compute 1 circled minus 2. For us, the obvious way would be to start at 1 and count backward, and we end up here at 15, and we cross the line, so we have an overflow. But again, the adder would have counted forward again by 14, so this direction, without crossing the line. So also in this case, we have to do this inversion. Of course, these are just two examples based on his pictures, so this is not a formal proof yet. However, the idea behind this picture is basically that this group is also a so-called finite cyclic group, so everything shown here also can be formalized. I'm sure you know how to fix our subtractor in Circuitverse so that it correctly indicates an overflow, like in the picture shown here. And also convince yourself that all the things that I explained for 4 bits easily can be generalized for n bits. So that, of course, we also can build a 8-bit subtractor, and maybe that's a nice assignment.